Hello, I welcome you all to your own channel MSK Learnium. In this video, we will solve the problem related to the heat transfer by using the finite element methods. So the problem on the screen, a wall of 0.6 meter thickness having thermal conductivity K is equal to 1.2 watt per meter Kelvin. The wall is to be isolated with a material of thickness 0.06 meter having thermal conductivity 0.3 watt per meter Kelvin. The inner surface temperature is 1000 degrees centigrade and the outside of the insulation is exposed to atmospheric air at 30 degrees centigrade with heat transfer coefficient, that is H is equal to 35 watt per meter square Kelvin. Calculate the nodal temperature. So you have one wall is there whose thickness is 0.6 meter and the thermal conductivity of that material is 1.2 watt per meter Kelvin, and that wall, that 0.6 meter of wall is insulated by a thickness of 0.06 meter whose thermal conductivity is this, and that insulating material is exposed to the atmospheric air whose temperature is 30 degrees centigrade and the air heat transfer coefficient is 35 watt per meter square Kelvin. The inner surface temperature is 1000 degrees centigrade, that is the wall temperature. At the inner wall temperature is 1000 degrees centigrade. We have to find out the nodal temperature, means intermediate temperature between the wall and insulation and the outside temperature of the insulation material, right? So the figure is like this, that when we draw the figure, this is the wall, right? So you can write this is the wall and this is the insulation, right? This is the insulation. This thermal conductivity K1 we can say that is 1.2 watt per meter Kelvin, and its thermal conductivity K2 is equal to 0.3 watt per meter Kelvin, right? So the thickness of this wall is 0.6 and the insulation is 0.06. So this nodal temperature, that inner surface temperature of the wall, that is T1. This is the intermediate temperature, we can say T2, and this is the outside temperature of the insulation material, that is the T3. Alright, and this insulation material is exposed to the atmospheric air whose temperature is 30 degrees centigrade and the heat transfer coefficient of the air is 35 watt per meter square Kelvin is given. You have to find out the nodal temperature, that is T2 and T3, by using the finite element methods. So how we will do? First of all, we will find the K1 and K2. For this K1, we can see only conduction takes place. Is it or not? Why? Because there is no fluid is involved in this, so there is a conduction. But in this material, when we find the heat convection for means a stiffness matrix for the element 2, there is a conduction as well as convection. So the combined equation we will use for element 2, but for element 1 we have only conduction. So let's start that. Here we'll go. First of all, we have a solution, right? And the given data we can write, given data right now. So this is what you have, a L1 is equal to 0.6 meter, L2 is equal to 0.06 meter, right? And K1 is equal to 1.2 watt per meter Kelvin and K2 is equal to 0.3 watt per meter Kelvin, right? That is inner surface temperature of the wall T1 is equal to 1000 degrees centigrade. Here the thermal conductivity is given in terms of the Kelvin, so we'll convert this, that is 1000 plus 273, 1000 plus 273, it will be 1273 Kelvin, right? Then we will find the T2, that is surrounding temperature, air temperature is given, which is 30 degrees centigrade. So it will be 30 plus 273, which is 303 Kelvin, right? And the heat transfer coefficient of air is given, which is 35 watt per meter square Kelvin, right now. So this data is given, we have to calculate, that is T2 nodal temperature is T2 is what, as well as T3 is what. right? So first of all we'll go for the element 1. So here we can write that for element 1, right? How the element 1 is look like? The element 1 is like this. This is the wall of having thickness is 0.6 meter. Alright, so this is 0.6 meter. This is the nodal temperature, inner surface temperature of the wall T1, which is given 1000 degrees centigrade, and this is the T2. This is the thermal conductivity K1. Only conduction will take place here. So we will write down the stiffness matrix for element 1, right? That is conduction stiffness matrix, you can say, right? Stiffness matrix, right? So when we have only conduction will takes place, the stiffness matrix formula will be, that is Ke we will use, and 1 for the element 1, right? So Ke1 is equal to A1 K1 by L1, 1 minus 1 minus 1 1. Actually that stiffness matrix basically we are denoting by K, but here K we will use for thermal conductivity. That's why to make a differences we are using Ke1. As you remember, if you, when you solve the problem for one dimensional bar element and the truss element problem, there will denoted the stiffness matrix by only K, but here we have a K is for thermal conductivity. That's why we are using the Ke1 only for heat transfer problem, right? So this is what you have, a Ke is 1 is equal to, that is area is not given, we will take unit area which is 1, and K1 is equal to 1.2 by 0.6, 1 minus 1 minus 1 and 1, right? So when you simplify, this value will come 2 and this 2 will multiply with this matrix. So the equation will become like this. Come back to the here, just hold on. So when we simplify that equation, we'll get the Ke1 is equal to, as I told you, we'll get 2. So 2 will multiply. So this is 2 minus 2 minus 2 and 2, right? We'll write down the boundary values also, that is this is associated with T1, T2, here also T1 and T2. This is row, second column, second row, first row, first column, second column, right? Now we'll go for the element 2, right? Element 2. So when you see the element 2 is insulation material and which is exposed to the air. So this is what thickness of the insulation material is given in the problem, which is 0.06 meter. Thermal conductivity of insulation material is given, which is 0.3 watt per meter Kelvin, and then this is exposed to the air, right? It is exposed to the air. So this is your air, right? Whose temperature, that air temperature T infinite is given 30 degrees centigrade, and the heat transfer coefficient is 35 watt per meter square Kelvin. Okay, now, so now what we will do here, if you look at, this is the temperature is T2, that is intermediate temperature between wall and insulation material, and this is the outside temperature of the wall, that is T3. So from T2 to T3 we have a conduction, but from T3 to air, that is the convection. So here the stiffness matrix formula will be changed, that stiffness matrix for element 2, that we can say Ke2 is equal to, first you have a conduction plus convection. So conduction convection equation will be like this, A2 K2 by L2, 1 minus 1 minus 1 1 plus heat transfer coefficient, that is for convection, HA, and you can find the convection is at the end, right? So here 0 0 0 1. You remember that if the convection is convection will be at the beginning, so this one will come to here and these three values will be 0, right? Now that problem also we will do. So then we can say here, now we have to substitute the values, that is Ke2 is equal to, area is unit 1 and thermal conductivity is 0.3 by 0.06, 1 minus 1 minus 1 1 plus H heat transfer coefficient is 35 into 1. These values are 0 0 0 and 1, right? So when you simplify, this will become 5. So 5 will multiply with these terms and 35 will multiply with this. So this equation will become like this, that is 5 minus 5 minus 5 also 5 plus this is 0 0 0 and 35. So when we simplify this equation, that simply you have to add. So this is stiffness matrix KE2, that for element 2 it will become 5 plus 0 is 5, minus 5 plus 0 is minus 5, minus 5 plus 0 is also minus 5, and 5 plus 35 will be 40, right? So this is how we will see. Then we can say the element 2 is associated with the T2 and T3, right? So here the nodal temperature, that is T2 and T3, this is T2 second row and third row, right? So now we have to we find the local stiffness for element 1 and element 2. Now we need to globalize them, means we have to add the element stiffness matrix 1 and stiffness matrix 2. So we can write that global stiffness matrix, right? Global stiffness matrix. So global stiffness matrix is what? That global stiffness matrix, we can say KE is equal to KE1 plus KE2, right? So simply we are adding these two matrices. So when we add these matrices, we can say that nodal temperature is T1, T2, T3. So the size of the matrix will be 3:3. As we know that how many nodes is there, that the size of the matrix will depends on that only, right? So here the 3 nodes, the 3 temperature is involved. So 3:3 matrix will come, right now. So you know how to add this. So this is what you have here, T1, T2 and T3. So similarly you have a T1 first row, second row and third row, right? T1 1 we will check, that is value is 2, right? So T21 is what we have a minus 2, right? T31 we don't have a T31, so it will be 0. We can check the KE1 and KE2 values right now. Then we have a T12 is also minus 2, but T2 you can see that this is the KE1, right? That is T2 T2, that is 2 here, and in KE2 also we have a 2, that is 5. So this 5 and that 2 will be added, okay? So this is what you have a 7, and T32 we have a minus 5, right? We don't have a 1 3, so it will be 0. 2 3 is also minus 5, and 3 3 is 40, right? So this is what the stiffness, global stiffness matrix we got, that is K. Now we have to formalize the finite element equation, that is KQ is equal to F. So here we don't write the Q. Why? Because the nodal displacement is not here, right? That nodal temperature is there. So we will write down the equation, that is KT is equal to F, right now. So here you have a finite element equation, right? Finite element equation. So this is the thermal problem. So the finite element equation will be KT is equal to F, right? K is the stiffness matrix, T is the nodal temperature, and F is the load vector, right? That is convective load vector basically, okay now. So here, so the K is equal to what? First of all we have to find out the convective force, right, from the free end. So we can say convective force from free end, right? From free end. So when we have a convection is there, we have to find out the load vector, that is force. That formula is F is equal to HA T infinite matrix of 0 1. Again I am repeating that in element 2 the convection is at the end, so that's why we are writing a 1 at the last, right? Now if the convection will begin, means at the starting the convection and then conduction, then you have a 1 0, okay? So here that formula, that equation will become H is equal to 35, area is 1 and temperature is 30. sorry, that is 303, right? So this will be, you have a equation that is 0 and 1, sorry, so 0 and 1. So this equation on simplification, this value will become like this, just wait, that this value will be like this, that is, this is 0, and so this is the 10.6 into 10 to the power of 3, right? So this is what we got, the load vector, that is convective force from free end. Now simply we have to solve the equation, that is then we have a finite element equation is what, that finite element equation we have written, that is k t is equal to f, right? So k we already got, that is 2 minus 2 0 minus 2 7 minus 5 0 minus 5 and 40, right? Nodal temperature we have a T1, T2, T3, right, is equal to F. F is equal to how much? That is, F1 is 0, F2 is also 0, and F3 is equal to 10.6 into 10 to the power of 3, that is convective force we got, right? Now, but that you know that at the node 1, the temperature is given, that is inner surface temperature of the element 1 is given, which is T1 is equal to 1000 degrees centigrade, means 1273 Kelvin. So means this temperature is known, that T1 is known, right? So this equation will be modified. How it will be modified? That whatever the node means the known temperature is given, that temperature at that point, at that means location, the force will be the value of the temperature, right? So we can write here the first row of force matrix is replaced by the known temperature at node 1, right? So here we can make a point that the first row of force matrix is replaced by known temperature at node 1, that is T1 is equal to 1273 Kelvin, right? So this equation, that T1 is known, so this T1 value we have to substitute at the force matrix at node 1, right, wherever the temperature is known, that point only. So here that equation will be will become like this, that is 2 minus 2 0, this is minus 2, 7 minus 5 0 minus 5 and 40. Then you have a T1, T2 and T3, right, is equal to what? Then the force matrix will be replaced. That is how, that at node 1 the temperature will be added, that is this 1273 and this is 0 and this will be 10.6 into 10 to the power of 3. Further that this temperature will also modified. So we can say the second row, first column of a stiffness matrix K is multiplied by a known temperature at node 1, right now. So we can say the second row and first column of a stiffness matrix K is multiplied by known temperature, right, at node 1, okay. So that is what, that is, you can say the known temperature second row and first column is this one, right? This is the second row and this is the first column. So that is the value, minus 2. So this minus 2 will multiply with the known temperature is what? Known temperature is T1, which is 1273. So that is minus 2 into 1273. So this value will become like this, 2546, right now, and this value will be added here. That is in force matrix, that is in second row, force matrix value will become like this, right now. So the modified equation further, it will be 2 minus 2 0 minus 2 7 minus 5 0 minus 5 and 40, right? And the nodal temperature is what? That is T1, T2, T3. The force matrix is equal to, F1 is replaced by that known temperature, which is 1273, and that F2 will become this value, that is minus 2 into 1273, whatever the value is coming, that is 2546, and this will be as it is 10.6 into 10 to the power of 3, right? So this is your equation, that is finite element equation is this one. Now as we know that we can solve this matrix by using elimination approach. So elimination approach means what? The boundary condition we have to impose. The boundary condition means T1 is known, so the first row and first column will be eliminated. So here we can impose the boundary condition. You can say apply the boundary conditions, that is T1 is equal to 1273 Kelvin is known, right? So first row and first column eliminated. First row and first column is eliminated, right? So when it is eliminated, let's eliminate them. So when we eliminate, it means the matrix will reduce into the 2:2 form, right? So first row and first column is eliminated. So the matrix is reduced in this format, that this will become like this, that is 7 minus 5 40 and T2 T3, this temperature we have to find, and that force is 2546, 10.6 into 10 to the power of 3, right? So we have a 2:2 matrix. This will become like this, that is 7 T2 minus 5 T3 is equal to 2546. Let's say this is equation 1. So how it is? This is this row and this column will multiply, right? Again this row and this column will multiply, that is this is minus 5 T2 plus 40 T3 is equal to 10.6 into 10 to the power of 3, equation 2. When we simplify these two equations, we'll get that temperature, that is T2 is equal to 607.31 Kelvin, and the T3 is equal to that is 341.03 Kelvin. So this is your answer. So this is how we will solve the problem, heat transfer problem, in finite element methods. Thank you.